Section: Introduction. In this section, we discuss the recent advancements in large language models, which have shown remarkable performance across various tasks, yet remain difficult for humans to understand. Our focus is on mechanistic interpretability, which seeks to clarify how these models operate. Much of the research in this area has concentrated on features, the specific variables that models use in their computations. Initially, attempts to interpret features centered on neurons, but we encountered challenges because neurons often respond to multiple, unrelated inputs, complicating their interpretation. One explanation for this complexity is the concept of superposition, suggesting that language models can represent more concepts than the dimensions they have available. To reduce confusion, the superposition theory proposes that features are represented as nearly independent directions within the model's hidden state space. We aim to separate these overlapping representations into distinct features by using unsupervised sparse autoencoders, SAEs, on the intermediate activations of language models. The effectiveness of this approach has led to a surge in research focused on scaling SAEs for advanced language models like Claude 3, Sonnet, and GPT-4. Despite scaling to 34 million features, we estimate that there are still many more features to uncover. Additionally, we find that larger models require more features to maintain the same level of accuracy in reconstruction. As model sizes increase, our current training methods may soon become impractical. Each training step for a sparse autoencoder typically involves 6 key computations: the encoder's forward pass, the encoder's gradient, the decoder's forward pass, the decoder's gradient, the latent gradient, and the pre-bias gradient. We introduce kernels that take advantage of the sparsity in the top K activation function to optimize all computations except for the encoder's forward pass, which remains dense. After applying these optimizations, we discover that the dense encoder forward pass limits training speed, while memory constraints arise from storing latent pre-activations. To address these issues, we present the switch sparse autoencoder, which we believe is the first solution to tackle both memory and computational bottlenecks. The switch SAE integrates the switch layer with the top K SAE, consisting of multiple small expert SAEs and a routing network that decides which expert processes each input. We demonstrate that the switch SAE improves training efficiency compared to existing methods. Our contributions include detailing the switch SAE architecture and comparing it to other SAE designs, outlining our training approach that balances reconstruction accuracy and expert usage, and establishing scaling laws for reconstruction error in relation to computational resources. We show that switch SAEs achieve lower reconstruction error than top K SAEs with the same training resources. We also benchmark switch SAEs against other models on the sparsity reconstruction trade-off and visualize the feature structure using T-SNE. Lastly, we confirm that the features from switch SAEs are as interpretable as those from top K SAEs. In the context of related work, we explore the concept of mixture of expert models, where only a subset of parameters is activated based on the input, allowing for more parameters without a proportional increase in computational cost. We discuss the sparsely gated mixture of experts layer, which was the first general-purpose conditional computation architecture, and how it has been used to scale models significantly. We also touch on deep learning training optimizations, which aim to speed up training through hardware accelerators and algorithmic improvements. Our approach differs from existing literature by not only focusing on speed but also ensuring that the quality of the SAEs is maintained. Section Summary. In this section, we discuss the challenges of mechanistic interpretability in large language models, particularly the issue of polysemantic neurons and the superposition hypothesis. We introduce the switch sparse autoencoder, which optimizes training efficiency and memory usage by combining expert networks with a routing mechanism, ultimately improving reconstruction performance while maintaining interpretability. Section: Sparse Autoencoder Optimizations. In this section, we discuss sparse autoencoder, SAE, optimizations. Since the early proposals of SAEs for separating model representations, we have seen numerous enhancements to the SAE architecture. These improvements include different activation functions like ProLU, top K, and batch top K, as well as architectural modifications to address feature suppression caused by the L1 penalty, and adjustments to the optimization goals. Various metrics are used to evaluate these enhancements, but we focus on the most common ones. The Pareto frontier of say latent sparsity, measured as average L0, mean squared error, and feature interpretability. We primarily compare our work against top KSAEs, as recent studies indicate they achieve top results on these metrics. For our baseline, we train sparse autoencoders to reconstruct language model activations, which we represent as vectors in a high-dimensional space. We break these down into sparse combinations of multiple unit-length feature vectors. The say architecture includes an encoder, a decoder, bias terms, and an activation function. The top K say produces a reconstruction of the input activation, and the latent vector indicates the strength of each feature's activation. Since this vector is sparse, we can optimize the decoder's forward pass effectively. The loss we measure is the reconstruction error, which is the squared difference between the original and reconstructed inputs. We also benchmark against the ReLU say, which uses the ReLU activation function and applies an L1 penalty for sparsity, and the gated say, which determines feature activation strength separately to avoid shrinkage. Next, we introduce the switch sparse autoencoder, switch say, which consists of multiple expert SAEs and a routing network that selects the appropriate expert for each input. Each expert resembles a top K say without a bias term. The router computes a probability distribution over the experts based on the input, allowing us to route the input to the most likely expert. This design helps us avoid heavy computations by using conditional processing. When training the switch SAEs, we train both the router and the expert SAEs together. We ensure the router is differentiable by weighting the output of the selected expert. We adopt various training strategies and enforce sparsity through the activation function of the top KSAE, optimizing the reconstruction mean squared error. Our training also includes an auxiliary loss that encourages an even distribution of activations across the experts to minimize overhead. The auxiliary loss is calculated based on the proportion of activations routed to each expert and the router's probability distribution. We aim for uniform routing across all experts. The reconstruction loss is defined as the average squared difference between the original and reconstructed inputs. We introduce a tunable hyperparameter to balance the auxiliary loss, and the total loss combines both the reconstruction and auxiliary losses. We optimize this total loss using the atom optimizer, setting the hyperparameter to a value of 3 in our experiments. Section Summary. In this section, we discuss various optimizations made to sparse autoencoders, SAEs, including architectural changes and alternative activation functions, focusing on metrics like latent sparsity and reconstruction error. We introduce the switch sparse autoencoder, which utilizes a routing network to select from multiple expert SAEs, and detail our training approach that balances reconstruction accuracy with uniform activation distribution across experts. Section Results. In this section, we train sparse autoencoders on the residual stream activations of GPT-2 small, which has a dimension of 768. The early layers of language models focus on detokenization and feature engineering, while the later layers enhance representations for predicting the next token. We specifically train sparse autoencoders on activations from layer 8, as we believe these contain rich feature representations that are not yet tailored for next token prediction. Using text data from Open Web Text, we conduct training for 100,000 steps with a batch size of 8,192, totaling around 820 million tokens. We first examine the scaling laws for switch sparse autoencoders, comparing them to dense top K sparse autoencoders at a fixed sparsity of 32. We present scaling curves of reconstruction mean squared error, MSE, in relation to both computational operations and the number of parameters for switch sparse autoencoders with 8 and 64 experts. Our findings indicate that switch sparse autoencoders scale more favorably in terms of computational operations compared to dense top K sparse autoencoders. Notably, Switch sparse autoencoders can achieve similar reconstruction MSE with significantly less computational power. However, they perform worse at a fixed width compared to dense top-K sparse autoencoders. Increasing the number of experts enhances computational efficiency but decreases parameter efficiency, which we believe is due to the need for features to be duplicated across multiple experts. Next, we analyze the performance of switch sparse autoencoders in terms of reconstruction error versus sparsity. We benchmark against ReLU, gated, and top-K sparse autoencoders under two conditions: flop-matched and width-matched. In the flop-matched scenario, we train switch sparse autoencoders with 2, 4, and 8 experts, each having 24,576 features. The results show that switch sparse autoencoders outperform top-K, gated, and ReLU sparse autoencoders in both MSE and loss recovery. As we increase the number of experts, performance improves while keeping computational and memory costs relatively stable. In the width-matched experiments, we train switch sparse autoencoders with 16, 32, 64, and 128 experts. Here, switch sparse autoencoders generally underperform compared to top-K sparse autoencoders in MSE and loss recovery, but they still outperform gated and ReLU sparse autoencoders in most cases. When sparsity is low, switch sparse autoencoders perform particularly well, suggesting that high-frequency features that enhance reconstruction fidelity may cluster together. Our results indicate that switch sparse autoencoders can reduce computational operations per activation by up to 128 times while maintaining the performance of a ReLU sparse autoencoder. We also believe that switch sparse autoencoders could achieve even greater efficiency with larger language models. We are curious about why switch sparse autoencoders have a worse reconstruction MSE than top-K sparse autoencoders of the same size. One possibility is that since only one expert is activated during each forward pass, some experts may learn duplicate features, which limits the capacity of the sparse autoencoder. We test this idea using a common evaluation metric, nearest neighbor cosine similarity. By measuring the proportion of decoder vectors with a nearest neighbor above a certain cosine similarity threshold, we can assess the presence of duplicate features. Our analysis shows that as we introduce experts, the proportion of duplicates increases significantly, indicating that strict duplicates may reduce the capacity of switch sparse autoencoders by up to 10%. This redundancy effect is less pronounced at higher sparsity levels. Additionally, we examine expert specialization, which reflects how similar the feature sets learned by each expert are. We quantify this by averaging the cosine similarity of features between different experts. If features are perfectly clustered, the similarity should match that of random blocks in a top-K sparse autoencoder. Conversely, if there is no specialization, the experts would be identical. Our findings reveal varying levels of uniqueness among experts, with some being quite distinct while others are more similar. Overall, all pairs of experts show greater similarity than random blocks in a top-K sparse autoencoder. Section Summary. In this section, we train sparse autoencoders, SAEs, on the activations of GPT-2's Layer 8, finding that switch SAEs outperform dense top-K SAEs in terms of reconstruction error and computational efficiency, although they struggle with feature redundancy due to duplicate features across experts. Our experiments reveal that while increasing the number of experts enhances performance, it also leads to a decrease in parameter efficiency, highlighting a trade-off in feature representation. Section T-SNE Visualization. In this section, we visualize the overall structure of sparse autoencoder, say, features using T-SNE projections of the encoder and decoder feature vectors. We observe that features from the same expert in the encoder tend to cluster together, while those from the decoder are more spread out. In the T-SNE projection of the encoder features, we also notice instances of feature duplication. Around the edges of the plot, there are isolated points that, upon closer examination, reveal tight groupings of multiple features from different experts. Next, we evaluate the interpretability of sparse autoencoder features through an automated approach. We generate explanations for each feature by providing the top examples that activate that feature to a language model. Then, we ask the model to predict, based solely on the feature's description, whether it activates for certain tokens in a new context. Recently, we introduced a more efficient method that assesses whether the explanation helps the language model determine if a feature activates at all in a given context. We also measure this detection across different levels of feature activation and in contexts where the feature does not activate, where the model should correctly indicate that the feature is inactive. From our findings, we see that features from flop-matched SAEs have a similar level of interpretability as those from top-K SAEs. However, width-matched SAEs show a higher true positive rate in contexts where the features activate, but they also have a lower true negative rate. We interpret this as indicating that switch SAEs may be biased towards having duplicate frequent features, which could make them easier to detect but also more likely to produce false positives.